Welcome back, students. Welcome to the course Natural Language Processing. My name is Priyanka Gupta. I am working as Assistant Professor in Department of Computer Science and Engineering in Data Science Department of Institute of Aeronautical Engineering, Hyderabad. I am going to today tell us about how to evaluate the different language model. In the last lecture, we have seen how the language model has been created. So now how to just evaluate the performance of the language model whenever we are having the huge document over there, huge data sets over there. So I'm going to tell you about how we are going to evaluate a language model. So two types of evaluations will be there. First is intrinsic and second is intrinsic. Then three measures will be there. Three matrices will be there. So first matrix is perplexity. Second is entropy and third is cross entropy. In perplexity, we will see how the perplexity is going to work for the different n-gram models as well as the language models, how to just measure entropy, how it will be used for the different fields in natural language processing fields, and how the cross entropy will be used. So let's start. How to evaluate different language models. So language modeling actually is the task of predicting the next word we can say the character or letters in a document. That can be used to train the language models. That can be applied to a wide range of natural language processing tasks. So basically in every natural language processing task, the language model will be applied. That is how all the tasks will be achieved. That is going to work on the, we can say, on the different models as well as on the machine learning models, right? So there can be the wide range of tasks like text generation, text classification, question answering. So these type of tasks will be achieved by applying the language models. Language models are very useful in the broad range of applications. Suppose speech recognition, machine translation, part of speech tagging, parsing, optical character recognition, that is OCR, handwriting recognition, and information retrieval. So these are the few applications are there in that this language model will be applied in the huge amount. Right? So the performance of language models in natural language processing is crucial to understand, and that can be evaluated with matrices like perplexity, cross entropy, and bits per character, that is BPC. So these few we can say methods are there. By applying those, we can just achieve the performance. We can just evaluate the different matrices. This type of we can say methods are going to let us build confidence whenever we are handling the language models in natural language processing, and whenever we are just we can say using different applications for different tasks, and that is also let us know if there are any places where the model may behave uncharacteristically. So whenever any problem is there in the model, whenever it is going to predict something about depending on the different task, the model is going to tell us many things. In practical, if we'll see, we need to decide on the data set to use. So on the basis of data set, it is going to give us the different outputs, different, we need to apply different models on that. The method to evaluate and also select a matrix to evaluate the language model. So first, we need to just choose the right data set, then we need to evaluate that, and then we need to, for that actually we need a matrix, we need a metric. How to evaluate a language model? So let us see how to evaluate actually. So evaluate a language model, let us know whether one language model is better than other model during the experimentation, right? And also to choose among already trained models. So that is the main goal of evaluating the different language models. A language model. There are two ways to evaluate language models in NLP. First is extrinsic, second is intrinsic evaluation. So what is intrinsic evaluation? That is going to capture how well the model captures what it is supposed to capture. Like if it is needed to calculate about the probability, is it doing that or not doing? So that it will be the intrinsic evaluation. Extrinsic evaluation is a task-based evaluation, is capturing how useful the model is for the particular task, for the particular natural language processing task. So these two evaluation can be just because they classify on the basis of different evaluation methods. Capturing among language models. So we compare actually models by collecting a corpus of text, right? So whatever we are just working on, we are working on the collection of the corpus, right? Collection is corpus is nothing, that is called as a corpora or document. So that will be common for models. That is going to be common for the models which we are comparing for. So if we are just suppose if we are comparing two of the models, for suppose one this corpus, a corpora, so the language model can be different, but the document or the we can say text will be same. We then have to divide the data into training and test data sets and going to train the parameters. On the basis of parameter for both the models, we have to just train the training set. We have to just train the data sets that is classified into the training part. Then after that, we have to compare how well the two trained models are going to fit the test data. So what is test data? That we are going to just check on that particular model. The new data, what it will come, how it is going to just check on the basis of feeded language model, feeded task. So whatever we are going to give, a new data set, on the basis of old data set, a historic data set, that is in the training data set, that is going to give the comparing, that on the basis of that we can do the comparing of that, comparison of that. Now let's see in broad what is extrinsic evaluation. So extrinsic evaluation is the best way to evaluate the performance of a language model by embedding it. So in that application, for that application or task we are using, we are measuring how much the application going to improve, how the accuracy of that particular application is. So it is an end-to-end evaluation where we can understand if a particular improvement in a component is really going to help us for the task at the last, at the end. Second thing, for example, if we are taking the speech recognition task application, we can compare the performance of two language models by just running the speech recognizer twice. Once with each language model and seeing which gives the more accurate transcription. So that will be for the second time, right? So these firstly we have to just check the language model, and second we have to check which model is doing, which model is working fine, how much accuracy each model is giving. So we need to take the advantage of extrinsic measures. Let's see intrinsic measures. So why? Because it is going to run on the big language model in the natural language processing system end to end, and going to give us very oftenly expensive, that we found it very expensive, and it is going to give us easier metric that can be used to quickly evaluate the potential improvement. So major improvement when we are comparing two models, it is going to give us very quickly. It is going to give us very quickly for the different language models. An intrinsic evaluation metric is one that is going to actually measure the quality of a model independent for the any of the application, any of the task what we are just doing and what we are working for. We also need a test set for a intrinsic evaluation of a language model in natural language processing system. The probability of a n-gram model, that is the language model, in that training set come from the corpus it is trained on. So on which corpus it will be trained on, for that only it is going to give us the probability. The training set of the, we can say, that is also called as a training corpus. So that probability of the language model will work only for that particular corpus, what we are going to just apply there, what we are going to use there for that language model. Now we can just measure the quality of n-gram model after that by its performance on the sum of the unseen test data sets. So that is called as a test set, a test corpus, right? That was the training corpus, a test set, training set. We will also sometimes call test sets and other data sets that are not in our training sets. That is held out corpora because we hold them out from the training data. So some of the time, we can say the validation data set also will be kept from the training data set itself, and we can use for the further other analysis. Good score during intrinsic evaluation don't always much better score during the extrinsic, or we can say intrinsic, both of them. So we can say we need both type of evaluation in practical. So any type of evaluation, any type of performance measure, we need both type of evaluation metric at least. Now let's see what is perplexity. Perplexity is a very common method to evaluate the language model on some of the held out data. So whatever data we are just keeping from the training set as we can say validation data set, that is in that we are just using the perplexity. That is one type of metric to just evaluate the performance of that particular language model. It is a measure of how well a probability model predicts a sample when we are giving the test data set, test corpus. Perplexity is also an interesting measure without the use of external data sets. That is going to evaluate the performance of language models which come under the natural language processing system. So the perplexity as a metric quantifies how uncertain a model is about the predictions it going to make. How the uncertain that is model, because it is going to just quantify, it is going to just predict the whatever the predictions will be there. For that it has been made, it has been applied. When we are having the low perplexity, that only going to give us guarantee that model is confident, not that is accurate. So that is how only we will be sure, we can say bit sure that is going to work fine. That is, we will have the confidence that is the model has been built in the right way. So we cannot say that is the accurate model for our different tasks for the language model. Perplexity is also going to give us a correlate well with the model's final real-time performance, and it can be quickly calculated using just the probability distribution. The model learns from the training data set. So actually it is going to work on the probability distribution, and that it is going to just calculate those probabilities on the basis of that particular different models and whatever the training corpus we have given on that basis, right? So perplexity often going to correlate those things, how well the model's final real world performance is going to work, and it is going to quickly calculate the probability distribution on the basis of training corpus. The intuition. So the basic intuition is that the higher the perplexity measure is, the better the language model is going to work. It is going to work on the unseen sentences or training corpus or data sets. Perplexity can also be seen as a single monotonic function of entropy. Entropy is also other type of measure that is going to just measure the performance of the language model. But perplexity is often used instead of entropy due to fact that the arguably more intuitive to our human minds than entropy. So whenever we are going to just apply different type of matrices, most of the time we use the perplexity. We will not use the entropy for that. Why? Because that is going to give the different we can say facts, and the perplexity is better work for the, we can say, monotonic we can say function, monotonic we can say key factor. So basically we will use the perplexity to just evaluate the language model. Perplexity, how to calculate perplexity of a language model, actually probability model, that is going to give us in NLP language model for a model for the unknown probabilities distributions. And a proposed probability model, we can just evaluate perplexity measure, that is a function, that is a one formula has been given, b minus 1 by n summation of I is equal to 1 to n log b q xi. So that is a formula. By that we can just we can say formulate, we can just get the perplexity of a model, of a language model. We can also choose b as 2. So we can also say 2 minus n by m. In general, the better models assign higher probabilities to the testing events. So whenever we are just using the test corpus, the higher probability it will get. So our model is working fine. Hence, the good models will have the lower perplexity values. So whenever the probability is high, that is going to give us the lower perplexity. That is how it works. And this is going to just going to give us less surprise by the test samples. So by this formula we can just calculate the different perplexities of the language model. If all the probability we will just have at least 1, so then the perplexity would be 1, and the model is would perfectly predict the test. Means that is very right for that particular language model, and that is going to give us summation of 1 probability. So means our model is working fine for that. Conversely, the perplexity will be higher for poor language model. So that is actually vice versa. Whenever we are having the good probability, we can say higher probability, the lesser perplexity we will get if the language model is working fine. If our language model is not working fine, our perplexity will be high and we will get the less probability. So that language is not working fine for that particular language model. Perplexity denoted by PP of a discrete probability distribution, small p, that is mathematically defined as small p, capital PP, in bracket small p, that is perplexity, that will be equal to 2 to the power capital H and in bracket small p. That will be equal to 2 to the power minus summation of R x small p x log 2 px. That will be equal to summation of x small px and at the power minus px. So that is a formula to how just to calculate the perplexity for the discrete probabilities, where a capital HP, that is called as a entropy in bits for the distribution, and x is the range over the events, which we will going to learn about further. So we will see later what are the different events will be there. Perplexity of a random variable, we can just denote as a capital X, right? That may be defined as a perplexity of the distribution over its possible values of small x. So that is how this discrete probability distribution formula will work. On other formulation for perplexity from the perspective of language models in natural language processing, it is the multiplicative inversion of a probability. In that case, that is going to assign to the test set, test corpus by the language model, and that is going to also normalized by the number of word in the test corpus, a test set. So in that case, we can define the perplexity mathematically as capital PP in bracket capital W is equal to capital P of W1, W2 to Wn, and that will be the power of minus 1 by n, capital N. That we can say equal to under root n and 1 divided by P, and that probability of small w2 to W capital N. That can be the formula of this multiple, we can say, inverse. We also know if a language model can predict the unseen words from the test set, if the capital P, that is a sentence from a test set, that will be highest in that time. So whenever that is going to give, whenever we are going to feed the unseen words, unseen sentences, in that case, that is going to work as a multiplicative inverse of that particular probability. So that is, in that case, it will be highest. Then such a language model is, in that case, it will be more accurate in that time. Now let's see interpreting how perplexity. Perplexity intuitively provides a more human way of thinking about the random variables uncertainty. So what is random variable? Whatever we can say, when we are applying the random function, that is going to take any random value, we can say from the different data sets, and that is going to give us uncertain value after that. So for that case, the reasoning in that, the perplexity of a uniform discrete random variable with capital K outcomes is capital K. For example, if I'll say the perplexity of a fair coin is 2, then the perplexity of a fair 6-sided die will be 6. Right? In this way, we can just quantify, we can say relate how the perplexity will be there. This kind of frameworks provide a frame of reference for interpreting a perplexity value. So here we have seen the coin is just referring the different perplexity. If we will say that same thing about dice, that is going to just interpret on the basis of that. So like that, these we can say references we can use to measure the different perplexity on the basis of this earlier given reference. Simple framework to interpret this perplexity. If the perplexity of some random variable capital X is 10, so our uncertainty towards the outcome of capital X is equal to the uncertainty. We would feel that towards a 10-sided die, helping us intuit the uncertainty more deeply. That will be equal to 10x only. Perplexity to compare different n-gram models, different language models. Steps to compute the perplexity for n-gram models. How to compute? So first we have to just calculate the joint probability of all the words in the sentence under the n-gram model. After that, we estimate the model parameters from the training corpus or training set. We will also then transform the joint probability into a perplexity for each of the sentence. How? By multiplying the probability of each word together. So we have to multiply each word perplexity together in that case. Then we first need to calculate the length of the sentence. In that words by including the end of the sentence, words as well as, then we need to calculate like perplexity is equal to 1 divided by power of sentence probability, comma 1 divided by sentence length. So that is a formula we will apply to just calculate the length of the sentence. Then we are going to calculate a single perplexity from the overall model. So if there are multiple sentences, then in that case we will do capital PP of capital W is equal to under root n 1 divided by P of S1, S2 to Sn. That is, n is capital there. Generic benchmarks and typical values of perplexity for n-gram models. If we assume a corpus of English, suppose that is having the vocabulary size of 50,000, we can establish a typical evaluation metric like we were using in the earlier lectures, unigram, bigram and trigram language models. After that, in a bigram model, if I'll say, each word depends only on the previous word in the sentence, while in the unigram model, each word will be chosen completely independently of other words in the sentence. So that in the that case, when we are applying the unigram model, the typical reported perplexity figures for such a data set, that will be equal to 74. And for the trigram model, it will be 137 for the bigram model. So 74 will be the bigram model, trigram model, and 137 will be the bigram model, and 955 will be for the unigram model. So the perplexity for a model that is going to simply assign probability 1 divided by 50,000. So that was the overall words there in that corpus for the each word, and that in the vocabulary, that would be 50,000. That I have said you, the 50,000 words we have taken, the vocabulary. Hence, the trigram model gives a big improvement. Why? Because overgram and unigram. So we can see here, that is going to give us the actually 74 perplexity. And both these bigram model, that is giving 137 and 955, that is not accurate. So how less perplexity will be there, the model is going to give the probability higher, and that is going to work fine. So we can say, for each models and for each task and application, the model is going to work differently. So which model will work fine, that we have to evaluate, but that we have to compare. So the perplexity of this model is going to assign the probability 1 divided by 50,000, right? So huge improvement over assigning a probability of 1 divided by 50,000 to each word for the vocabulary 50,000. Perplexity, how it will work in the real world. Perplexity is used as a measure in training data language models that is related to standardized data sets. So some standard data sets are there, that is 1 billion word benchmark. That data set actually was collected from the thousands of online news articles that was published in year 2011 actually, all broken down into the complete sentences. So in that case, that component sentences, perplexity as a metric measures how accurately a model can mimic, how it can work fine. The style of the dataset, it is being tested against the model trained on the dataset from some period as a benchmark. Dataset have an unfair advantage, that due to vocabulary similarity. So because in this dataset actually some vocabulary was similar and may not work then testing for different time periods, and that is slightly different data sets even though they are working in the same domain. So that actually will work, that will depend on the data set also, and the data set's vocabulary also, how the perplexity is going to work on that, how it is going to just give the right less perplexity out of that particular language model. So perplexity also rewards models for mimicking the test data set, and it is going to end up favoring the models most likely to imitate subtly toxic content. So if we are having the toxic content, if the dataset is related to freely flowing language like a text from social media, so that is unpredictable data, we can say text from the social media, and that is called as a toxic content whenever it is going to give us freely flowing language. That is going to study about, about the content is more polarized, that all the content can be different polars for each sentences. That is going to give us that easily discussed compared to non-toxic topics. So that is the perplexity in the real world. What will be the pros and cons? So advantages of using perplexity: fast to calculate, and hence this is going to allow researchers to select among the models that is unlikely to perform well in the real world scenario that we have seen, where computing its probability costly and testing is time consuming and that is going to expensive also. So this is first advantage. Second advantage is that is useful to have an estimate of the model uncertainty, or we can say information density. These two advantages are there. Disadvantages of perplexity. First is not good for final evaluation, since it is going to just measure the model's confidence and it is not going to give us actual accuracy of the model. Second is hard to make comparisons, because different data sets with different context length, different vocabulary size, words, character based models. In that case, it is not going to give us right comparison. Third is perplexity can also end up rewarding the models that mimic outdated data models or data sets. In that three cases, it is going to give us these disadvantages. Now let's see what is entropy. Entropy is actually a metric that is going to used to quantify the randomness of the particular process in many of the fields, and going to compare worldwide languages, specifically in computational linguistic science. So definition will be for entropy is the entropy, also called as a self-information of a random variable, that is going to give us the average level of the information, surprise of certainty inherent to the single variable's possible outcome. The more certain, a more deterministic an event is, the less information it will contain. So that is a proper definition of the entropy. In the net scale, the information is a increase in uncertainty or entropy. So actually it is also called as an uncertainty. Entropy of a discrete distribution, that is small p of x over the event space, that is capital X, is going to give us capital H of p is equal to minus summation of x to capital X, that is px and log px. That is a formula that will be used to just calculate the entropy for the discrete distribution. Here the h of x will be just more than or equal to 0. H of x is when h of x is equal to 0 only when the value of x is indeterminate, and hence it is providing no any new information from the different models. The smallest possible entropy for any distribution will be 0 itself, and in that case it will be indeterminate. We also know that the entropy of a probability distribution will be maximized when it is going to have the uniform distribution. So this is how entropy will be measured. How the entropy will be just used in the different natural language processing fields and AI, artificial intelligence. In terms of probability theory, the NLP, language perspective and probability theory, according to the NLP, entropy can also be defined as a statistical parameter that measures how much information is produced for each letter of a text in the language. If the language is translated into binary digits, that is from 0 or 1, in the most efficient way, the entropy capital H is the average number of binary digits that will be required per letter of the original language. That is how the that will be just denoted, that is referred. From a machine learning perspective, entropy is a measure of uncertainty. So these two we can say definitions are there for perplexity, entropy for each other. And the objective of machine learning model is to minimize the uncertainty. So these two cases, the entropy will work. Decision tree learning algorithm use relative entropy to determine the decision rules that is govern the data for each of the node. So that also we have seen in the form of knowledge tree, that decision tree actually same as a knowledge tree actually, but for each we can say node we have to calculate the entropy, that is relative entropy. Classification algorithm in machine learning like logistic regression or artificial neural networks often employ a standard loss function called as cross entropy loss, that is going to actually minimize the average cross entropy between ground truth and the predicted distribution. So that is how the entropy will be work for the different natural language processing fields and AI machine learning fields. What is cross entropy? Cross entropy word came in the last slide. So due to the fact that we can't access an infinite amount of text in the language and the true distribution of the language is unknown, in that case we define a more useful and usable metric that is called as a cross entropy. In that case we are going to just calculate the measures, how close they two are. Intuition for cross entropy is if often used to measure the closeness of two distributions, where one distribution is from the sample text Q, that is capital Q, that the language model aims to learn with as much proximity as possible, and the other is the empirical distribution of the language, that is capital P. So mathematical cross entropy will be calculated as defined as capital H of P comma Q is equal to EP, and that will be in the bracket minus log Q, which can be also written as capital H of capital P comma Q, that will be equal to H of P, H of capital P plus D of KL, and that P is equal to Q. In that case, H of PQ will be the entropy and D of KL PQ will be the pullback Lelber-KL divergence, that is from the Q from P, right? So it is also known as the relative entropy with respect to P is respect to Q. From the formulation, we can also see that the cross entropy of Q with respect to P is the sum of two terms, that is entropy plus relative entropy, right? So where H of P in the latter second formula we have seen that is that first we are adding the entropy and the relative entropy. So HP will be the entropy for P, is that will be the number of bits, that will be the average number of bits that is needed to encode any possible outcomes of capital P. The number of extra bits that is required to encode any possible outcome of capital P optimized over capital Q, that will be achieved by that pullback Lelber divergence model, right? So the empirical entropy, that is capital H of P, is unoptimizable, and so when we train a language model with the objective of minimizing the cross entropy loss, and that is going to give us the true objective how to minimize the that KL divergence of the distribution, which was going to learn by our language model from the empirical distribution of the language. So that is how the perplexity entropy and this cross entropy is going to work on the different language model, and how it is going to just evaluate what are the processes are there, how it is just depend on the probability, how it is going to work for the real world scenario applications we have seen. So that was for today topic. Thank you for watching.
Like, share and subscribe. Hit the bell icon for more updates.